The topic of this series of videos is mutagenesis, and it's probably best to start with a definition of that. Mutagenesis simply refers to the induction of errors or mutations in DNA. Now, we spoke earlier about how errors are very rare in replication because of the accuracy of the DNA polymerases and also because of their proofreading activities. But nonetheless, we can end up with approximately 1 in a billion errors that accumulate in DNA chromosomes. So the first thing I'd like to do is to discuss the definition of different types of mutations, and then we'll go on and talk about causes of mutagenesis that occur from environmental or other sources. So let's get into the types of mutations. First of all, we have point mutations. These are the most common to form, and these are when you have single base pair changes. These happen in two different ways. The most common is transitions in which you have a purine changing to another purine. For instance, A becoming G. Alternatively, you might see a pyrimidine becoming a pyrimidine, like a C changing into a T. Less common is transversions in which a purine, the two-ring system, is changing into a pyrimidine, the one-ring system, or a pyrimidine is changing into a purine. And lastly, we have the least common but very important insertions and deletions in which we have the addition or removal of one or more base pairs. Okay, with those definitions behind us, I'd like to get into the first of 4 causes of mutagenesis. And the very first one we'd like to do is spontaneous transitions, and that is most typically going to be C to T. And again, this is something that happens constantly. There is no cause of it. It just is going to happen all the time in your DNA, not even during replication. I will note that it can be catalyzed or aided by the presence of acids. And we'll see why in just a moment. Okay, let's consider cytosine, the base, the pyrimidine, and its exocyclic amine. This can undergo a spontaneous tautomerization that we have seen in the past. We're going to see a pair of electrons on this nitrogen flip down to form a double bond, and the double bond in the ring can flip out and pick up a proton. And like I said before, that can be aided if there is a little bit of acid floating around in the nucleus. When that happens, it's probably worth having you pause the video here for a moment, and right up here in this area, I'd like you to draw what this is going to look like as cytosine in the alternative form that we just laid out with those arrows. So take a moment and do that, and we'll come back and see what it looks like. Okay, I hope that wasn't too hard for you, but let's see how you did. Cytosine can form this alternative structure, which is a tautomer of the normal form that we have below. And in the alternative tautomer, we have a double bond to the nitrogen outside the ring and a single bond in the ring where there was a double bond before. And this nitrogen that is still here as part of the pyrimidine ring is now protonated, as we noticed, catalyzed by that acid. Okay, I want to make sure to remember that I have a positive charge on that nitrogen, and you may recognize what we have here, one of our old friends, an old theme, and that is we have a Schiff base, and Schiff bases can be spontaneously hydrolyzed or resolved by the presence of water. So we'll go ahead and do that. We'll skip any involvement of acids and bases and just cut to the chase. You may remember we do a double attack from water, and that will allow the splitting off of an ammonia, and we end up forming, as we can see right here, a carbonyl. Now, when we transition a nitrogen to a carbonyl, that actually makes uracil, and uracil is obviously one of our normal bases that we have in RNA. So what we can see here is a cytosine has become a uracil, but remember earlier I said it's a cytosine becoming a thymidine. So what's the deal with that? Well, let's note that if a cytosine becomes a uracil, in the next round of replication, the uracil will be paired with an adenine or adenosine. So let's consider that a little bit. First of all, we have a CG base pair. We'll call that the original. And then if we undergo spontaneous hydrolysis, we end up with a U mispaired to a G, and in the next round of replication, as I said a moment ago, that U will end up being paired with an A, because U's always go with A, even if it's in DNA. And then we do another round of replication, and that A will become paired with a T, because normal replication would put a T next to an A. And so what you can see is after the spontaneous hydrolysis and 2 rounds of replication, the CG base pair has become a TA base pair, and we have a net transition. It's worth noting that this can also happen with adenine, which has an exocyclic nitrogen here, and through tautomerization and spontaneous hydrolysis of the Schiff base, we can end up with a hypoxanthine, which is not a normal base, but that will pair with a cytosine, which will ultimately result in an AG transition, which is very similar to a CT transition. Okay, we'll pick up the next cause in the next video.